So for the quiz on Friday, there'll probably be 10 or 12 questions. But like I said, I'm going to give you extra time. And I'll give you like extra time. I'll give you more than you need. But I don't want to give you so much that you're just going to be hanging around waiting for people to finish, because I have to wait for the time to complete before you can go. Okay? So it's not going to be as rushed as it was before. You'll have extra time. If you want to bring a book, you're welcome to bring a book. You can't scroll your phone, okay? But if you have a book, you can pull that out and look at it. Okay? Mainly exam 3, when you're looking at old exams, I think like fall 2018, for example, is all chapters 5 and 6. Anytime you're looking at things that have to do with energy, like you're going to see one of these types of problems, number 2 or 3. We can come back and look at these. You see spring problems, that's the F equals kx, and the PE is 1/2 kx squared, elastic potential energy. You'll see work energy problems or work problems. Don't worry, we'll come back to these. And then the other part is going to be on momentum, like number 21, for example, here. Here's a momentum problem. And remember, those are 2 types of problems. Write this down. So for chapter 6, you have these 2 types of problems where just calculating momentum, P is equal to M times V, either for a single or multiple system of multiple particles in a system. Doing the force, which is delta P over delta T, like the collision, the car running into the wall, what was the force that was that acted on the car in order to cause that change in momentum? And then also doing conservation of momentum, PI equals PF. Okay, just like the ones we did today. And you're absolutely going to see one of these, a collision, on Friday, because it's going to be on the test. I just want to make sure that y'all get a lot of practice at it. And you could see some of the others too. Chapter 5 again, just calculating work. Work is FD cosine theta. Showing that work causes a change in energy, and then doing the conservation of energy, EI equals EF. Those are the big major topics from chapters 5 and 6. Work energy theorem, conservation of energy, momentum, the Newton's second law, that's the F equal delta P over delta T, and then conservation of momentum, elastic and inelastic collisions. Okay, you want to just go through some problems? We'll look at some chapter 5 problems, and then we'll look at some chapter 6 problems. I'm going to do them sort of side by side here. You want to do a roller coaster type problem here, like this one? All right, number 3. Gosh, have we done this fall 18? I don't think we've looked at fall 18, have we? I think we have. Okay. So I have a bit of a headache today. You ever get headaches? All the time, right? No, you shouldn't get them all the time. If you get them all the time, something's wrong. Like you need to revisit your life. But I understand. Sometimes we just do that. So here I have this bead has a mass of 1 kilogram, which I think I can write on the screen here. Bead has a mass of 1 kilogram as it rests at point A. The rest is a really important idea because that tells me that the kinetic energy up here is equal to 0. So it only has potential energy. And then I want to know what is its velocity at point C. Look, because it's at a lower position than it is here, I know that at this point it is going to have kinetic energy, right? Because right here it has no kinetic energy, all it has is potential energy. It's never going to rise above this height. So even if it went all the way over here, it would only rise up to this height because that's all the potential energy that it has. But at point C, it has both kinetic and potential. And so these problems are just first identifying what type of energy is where, and then just setting those equal. So PE at A is equal to KE at C plus PE at C. And so that's going to be MGH A equals 1/2 M V squared. That's at location C, which is what we want to know. We want to know the speed at point C plus mgh at point C. Notice the masses all cancel out. Unless you're dealing with springs, That will always be the case, right? Because the springs, you don't have a mass in the elastic potential energy equation. Unless you're dealing with springs, the mass will always cancel out. Even if I give it to you, you don't need it. Okay, so I'm going to put some numbers in here. 10 times 5, that's 50. Look, I did 10 times this value, g times h. And I said g is equal to positive 10 meters per second squared. Always use g as positive. A lot of you are still using g as negative. But remember, when we're talking about the acceleration due to gravity, it's equal to negative g. G is always a positive value. It's always positive 10. Okay, that's equal to 1/2 VC squared. That's what we're looking for. Plus G times 2, or 20. I multiplied positive 10 times H at location C, which is 2 meters right there. And so I get, I subtract 20 from both sides. 30 equals 1/2 V squared. I multiply both sides by 2 to get rid of the half, so that's 60 equals V squared. And then I take the square root of both sides. So it's the square root of 60, which is somewhere between 7 and 8. Oh, so it's going to be B. Right, because 7 squared is 49, 8 squared is 64, so it's somewhere between 7 and 8. Okay? Yeah. You should also be able to find the velocity at point B. I know that at point B it only has kinetic energy. So if I asked you for the velocity at point B, it would be exactly the same, except for this equation would be different. How? How would this equation be different at point B, other than replacing the C with a B? But what else is going to be different? Right. This term is going to go away. No potential energy. So whenever you encounter these problems, the first question you ask is, what kind of energy does it have? Like, for example, here, we're not going to work it, but let's just sort of think about what kind of energy does it have where? What kind of energy does it have up here? Okay. Yeah, V is equal to the square root of 60. Wait. Yeah, that's the square root. Right here?
No, that's true, because it's equal to squared under the...
Oh, yeah. Yeah, sorry. So right here, it has potential energy. Anything else? To read the problem carefully. So it says at the top, the block has a downward velocity. So since it has a downward velocity, in fact, that's what we're looking for, it also has kinetic energy. And then at the bottom, where I know its speed, it only has kinetic energy, no potential energy. And we set those two equal to one another and solve for the velocity or the speed. There we go.
At the bottom, it doesn't have potential energy.
Right.
It's at the top and at rest, it doesn't have kinetic energy.
Right. So your question always is, what is H? And then what is V? And if H is 0, potential energy is 0. And if V is 0, kinetic energy is 0. That's always the question you're asking. What is H? What is V? And we're always, H is actually a relative term, the height. But for our purpose, we'll always let ground level be H equals 0. But H is a relative term. We could say that H right here is equal to 0. We're not going to do that. It just makes it more complicated than it needs to be. So we'll always say that here, at ground level, H is equal to 0. Okay? All right, let's look at some others. Okay, I like number 5. If it's not on the quiz, it'll be on the test. A cardboard box of unknown mass is sliding upon a horizontal frictionless surface. The box has a velocity of 6 meters per second when it encounters friction. It slides 2 meters, and then the box has a velocity of 4 meters per second. What is the coefficient of friction for the surface? This would fall under the category of those problems where work equals change in energy. Because in this case, I have a box with a certain amount of energy, and then it encounters a frictional force, and then after it encounters that frictional force, it has a lesser amount of energy. And so it would work out kind of like this. The work done by the frictional force is equal to the change in energy. And the change in energy, E final minus E initial, will equal to the work done by the frictional force. E final is going to be kinetic energy final. E initial, it only has kinetic energy. In fact, in these problems, you'll only be dealing with one type of energy, usually kinetic energy. Will equal to the work done by friction. Yeah, Ariel?
How can you tell, like, what's the potential?
Oh, if it was potential, the object would be changing height. But here it's only changing speed, not changing height. Okay? But if it's dealing with friction, it's always going to be kinetic energy because it's going to be, the friction will change the speed of the object. It'll slow it down. Need to recognize too here that the work done by friction is negative. I can tell that because I know that this final kinetic energy is going to be less than the initial kinetic energy. So this value is going to be negative because this is a small number, this is the big number. And so this needs to be negative too. But the work done by friction, because the force and the displacement are opposite directions, that work is almost always negative for frictional forces. Follow me? We cool? I can slow down if you like. If you have questions. Okay. All right. Let's. So kinetic energy final is going to be 1/2 mvf squared minus 1/2 mvi squared. I don't have the mass. It's an unknown mass. Is equal to Fk. What is Fk? Well, Fk I know is mu k times the normal force times d. But further, I know that the normal force, oh, I can't get rid of that. The normal force is actually equal to the weight, or m times g. I just substituted there, said that the normal force is equal to the weight. And then my masses all cancel out because I have a mass in every term. Remember, I have to have a mass in every term. I divide through every term to get rid of the mass. And then I solve that for mu k. I know everything else. I know all these values. So let's just put in some numbers here. I have Vf is 4. Vi is 6. Mu, I'm looking for that. 10 meters per second squared, that's g. And then d is 2 meters. 16, or half is 8 minus 18. Is that right? Shoot, I don't know. So it's 1/2. We did a problem like that in class, but it's a useful problem. I think the problem that we did in class, the object was actually coming down an inclined plane. But you have to figure out what is the work done by friction. And then subtract that work. Think of it, oh, that frictional force is taking away energy from my object. It's probably one of the more complicated questions for this test. Like, I think the others, if you practice them, they're not so hard. But this one, if you practice it, it's not going to be hard. Or you're going to do it just fine. Because they don't really change up that much, frankly. They're all a lot the same. If you don't practice, it's not going to do it. Okay. This is a elastic potential energy problem. You can see one of these. If not on the quiz, you'll see it on the test, where we're dealing not with just gravitational and kinetic energy, but also elastic potential energy. And remember, you'll have your equation sheet on Friday, but I find that, you know, the students that make A's usually know the equations anyway. There aren't that many equations, honestly. So PES is 1/2 kx squared. Here, I have a spring-loaded gun. It shoots a 0.2 kilogram steel ball. You compress the spring, by this amount, and then it has a spring constant of 250, and I want to know the speed of the ball. So this is the setup. I have this spring all loaded up. It's like in the lab. And then it shoots. The spring decompresses. It goes back to its equilibrium position, and the ball gets some velocity. Just like with the roller coaster, I want to know what kind of energy it has. What does it have here? Kinetic, elastic, or gravitational potential energy? Kind of energy. Right here, where the spring is all compressed up and it's not moving. A potential, right? Gravitational or elastic potential. You know, y'all know. Come on, you know. Elastic potential, right. Right. So it has elastic potential energy here, and then after it shoots the ball, the spring is now at its equilibrium position at x equals 0. So no more elastic potential energy. That's all expended and given to the ball as what type of energy? Kinetic. Right. So what I'm doing here is I'm taking the elastic potential energy, 1/2 kx squared, and making it equal to 1/2 mv squared. And then I'm solving for v. I know all those values, but if I solve for v, I can do that. Now, a similar but slightly different problem, I don't think I've given this on a test before, but I absolutely could. Oh no, number 11 is similar. Let's just look at number 11. So here, I'm just going to write solve for v. Cool on solving for v? That algebra? Okay, I'm not going to do it then. Number 11 is a very similar problem, except instead of the elastic potential energy turning into kinetic energy, it's turning into gravitational potential energy, or vice versa, actually. I have an object, and it falls onto a spring. Here, it only has gravitational potential energy, and then it falls onto the spring and compresses it. Here, it only has elastic potential energy, PES. So we set those two equal. mgh equals 1/2 kx squared. And I solve for, I'm looking for x. I solve for x. That's this distance. By how much does the spring compress? Actually, if we want to be clear, it's actually this distance. By how much have you compressed the spring from the equilibrium position? If I was long here, and then it's shorter by a certain amount, because I've compressed that spring down when I drop this object onto the spring. And then I can, potential energy here, I can find out how much it's compressed that spring to give it elastic potential energy here. These problems are all alike. You're looking at the type of energy that's involved, and then you're just setting it equal to one another. But identifying the type of energy might be the most difficult part. And then you have to figure out, just do it in algebra to figure out what it is. Y'all should be okay on the algebra. I know not everybody is, but by this time of the semester, we should be okay on the algebra. Right? You're okay on the algebra? It's important that you are. All right. Let's look at some momentum problems. Is that okay? Are there particular problems you want to look at? Remember, need to look at some of these conceptual problems. I'm not spending much time on them, but make sure that you quiz yourself on those too. If you read over them a few times, I think you'll probably remember the answers. No surprises. I'm going to pull straight from old exams and probably just like the last, say, 4 or 5 old exams. I'm not going to go back to like 2005. So look at those old exams. I'm sorry, y'all writing that down? That might not be true. I could go back that far, but most likely I'll stick to the most recent exams. All right, I'll stick to the last 5 years just because I said that. But in the next quiz, that might not be true. I'm just saying that for now because I just said that. Okay? But anyway, make sure that you review these. Just sort of read through them and, quiz yourself on them. After you do it a few times, you'll be getting them just like that, okay? Let's look at, that's all conservation. That's all. Oh, here we go. Okay, so a couple things. Number 24 here, what is the impulse? Impulse is really got to know what impulse is, right? Do you remember what impulse is? It's just a fancy word for what? Change in something? Yeah, but that's, oh no, that's the force. So impulse is equal to a change in momentum. All right, F is equal to delta P over delta T, but I is equal to force delta T, but that's equal to delta P. Actually, I think to be technically correct, when they talk about impulse, they're talking about the product of F delta T, because it's the interval of that F versus time graph, but it's the same as their delta P. So here, if I want to know the impulse, I is equal to P final minus P initial. Remembering these are vectors, but I have the signs here on the velocities. And then I have 2 kilograms. Tricky part is knowing which is which. The final is going from -4 to +3. So the final is the +3 meters per second. It's not hard if you think about it just for a few seconds, but you know, take just a moment, take a big deep breath and say, okay, what's my initial and what's my final? Minus 2 times -4. 6 plus 8 equals 14. So 14 is the right answer. I want you to notice what would happen if you got these final and initial mixed up. Like if you had 4 here, or -4 here, and 3 here, I would have 2 times -4 would be -8. -6, would be -14. Okay, yeah, that's not a big deal. Just be careful with your signs, okay? Make sure that you're watching your signs. Let's look at this collision. You're going to have a collision problem. So you'll have one of those roller coaster problems. You'll also have a collision problem. And it'll be similar, very, very similar to one of these. If you look back at old tests, every test has almost every test has a figure that looks like this. And I just ask you, what is the final velocity of one of the particles? And so I do that by setting the momenta equal to one another. Pi equals Pf. I know by conservation of momentum that those two have to be equal to one another. Before and after, the total momentum has to always be equal. And that's always, always true, no matter what you're dealing with, that the momentum will always be equal. These are systems with multiple particles, and so I just add up all the momenta for each particle. P is equal to mass times velocity. And so I have 1 kilogram times 2 meters per second plus 2 kilograms, watch your signs, minus 1 meter per second. And then that's going to equal to 1 kilogram times -1 meters per second. I got that from right here. Plus 2 kilograms times VF. That's V2F. And then I solve for that. Got to watch your signs on these, because if you get your signs, you're probably going to get the answer wrong if you do your signs incorrectly. Oh, goodness. Let's see. That's 2 minus 2, so this side is 0. -1 plus 2 V2F. So V2F has to be 1/2. But again, watch your signs. If you get your signs wrong, you're going to miss the problem. That's the biggest mistake on this chapter especially, is just getting the signs incorrect. And the reason you have to watch that is because they're vectors, and the signs give direction. Okay, the other problem is like number 23, and that's a force problem, a Newton's second law problem. Can I clear this out? Okay. For how long should a force be applied to change its speed from 20 to 30, and I give you its mass? This should be a simple plugging in the right equation. F is equal to delta P over delta T. I can expand that. MVF minus MV VI divided by T. And I'm looking for T. So I'm just going to say T is equal to M, which is 25 times VF minus VI divided by the force, which is 100. So it's 25 times 10, 250, divided by 100, 2.5 seconds. It's the other type of problem that you'll have. And that's it as far as calculations. But you know, on a 10-question quiz, you'll probably have 3 calculation problems. One of them's going to be momentum, conservation momentum problem. One of them's going to be a roller coaster. And I don't know what the other of these would be, one of these other types. Okay? Others y'all want to look at? Others in particular?
Can you look at some of the, like, just the word
Yeah.
ones that are just like confusing?
Like this, who is awesome? I like this one. Kim Jong-un. Are you those people who kick puppies?
You pick the worst people.
Okay. Let's see. A rubber mat will decrease the force of impact if an object falls onto it. Why is that? We talked about this. This is the same as the idea of the bumper on the car. That the bumper on the car collapses, but why does that decrease the force? F is equal to delta P over delta T. If I want to make that force go down, I can make either this go down or I can make this go up. But if you're in an accident, it's hard to make this go down. Like your velocity is what your velocity is. But you can change the time over which the impact occurs. And so you make delta T go up, and that makes the force go down. And the rubber mat is the same. If I drop something onto a rubber mat, say an egg or whatever, when it hits the rubber mat slows it down, and the impact occurs over a longer amount of time. Probably going to see something like this, okay? Oh, let's see. Okay, so if I have a particle of mass m, that means m doesn't change, okay? It is what it is. But if I double its momentum, I know that momentum is m times v. To double this particle's momentum, I will have had to double its velocity. And so now I'm asking, if you double its momentum, what have you done to its kinetic energy? And now we say kinetic energy is 1/2 mv squared. If I double its velocity, which is what I had to do up here to double its momentum, I quadruple the kinetic energy. So D is the right answer there. Those types of questions you'll see on the test, or on the quiz and on the test. Need to know power. That's just a definition. In fact, it's on your equation sheet. It says power is work divided by time, or I think it says energy over time on your equation sheet. Just be familiar with your equation sheet. I would print it out, just sort of keep it in a familiar place, post it on your cupboard or wherever it is that you put things that you look at a lot.
So we don't have any calculations with power?
Yeah, you could have a calculation, but I'm not that concerned about it. It would be really simple. I would just say so-and-so does 10 joules of work in 5 seconds. What is the power? And then you would say 10 joules divided by 5 seconds would be 2 watts. Okay, we're going to see power again next semester, so I'm not really that concerned about it. Y'all get to take this class for a whole year. Actually, yeah, y'all take it. Geomatics. The second semester is really the most important semester because we get into fields. I know you guys talk about gravitational fields in your geodesy classes, right? Gravitational fields and geodesy. Oh, you haven't taken it. And then
what is that, gravitational fields?
yeah. Okay, a box slides towards you and you stop it. How do you describe the work you did on the box? If I'm stopping it, I'm taking energy away from the box, so that's negative work. Yeah, this is a good test. There's the expression for power, or it says work over time.
What were those equations with joule?
What now?
Those equations with like that, with like joules.
Right here? What is the work done by the gravitational force? Okay, so the gravitational force acts in this direction. That's Fw. And the work done by that is going to be 0. The reason it's 0, because work is equal to force W times the displacement, which is going to be Y. But there is no displacement in the Y direction for this object, because it's just moving along the horizontal direction. All the displacement is in the horizontal direction, not vertical. Yes? Cool. Okay. All right. Let's look at a couple, well, maybe one other exam. If you have burning questions, we can answer them. Let's just see if there are any that stand out. A lot of these are similar. Can we do number 2? Number 2 is a similar one. The work energy, right? Work equals change in energy. I have a 10-kilogram kid, comes down a slide. The slide is 2 meters high and it's 4 meters long. The slide has a frictional force of 5 newtons that acts along the entire length of the slide. So here's the kid. We'll just draw him as a block. At the top, he only has potential energy. At the bottom, he has kinetic energy. But in between, he has the work done by friction. So as he's sliding down, and that work done by friction is taken away from him. So the potential energy minus the work that's taken away from him will be equal to my kinetic energy at the bottom. You'll see how I wrote that? He has some potential energy at the top. As he slides down, the frictional force takes away energy from him. And then what's left when he gets to the bottom is the kinetic energy at the bottom. That's it. That's sort of my framework. I have mgh minus the frictional force times the distance equals 1/2 mv squared. I think I know all this, actually. Yeah, everything's given. You got to make sure that you get the right distances and heights and stuff. So let's go ahead and put in the numbers. That's a little tricky. mgh, 10 kilograms, that's his mass, times 10 meters per second squared, times h, it's 2 meters high, minus Fk, which is 5 newtons. Okay, now Fk acts over the length of the slide. So you don't use 2 meters here. Here we use 4 meters. That's the length of the slide. And then that's going to equal to 1/2 mv squared. 1/2, the mass is 10 v squared. It's 200. 200 minus 20, 180. Oh, what's that, 36? So V is equal to 6 meters per second. Okay. That type of question is probably a good one for the quiz. It's probably one of the harder of them, so good to get practice on it now. Wink, wink, I think. Pretty sure we'll do that. Y'all hear me? Roller coaster type problem, or like the bug here, that's a similar one. Collision, and then probably one like this. Okay. Some stuff about conservative versus non-conservative forces. Conservative forces conserve energy. Conservative forces are path independent. Do not depend upon the path. Kinetic energy, there's power. A lot of this is the same as the previous. You move 3 identical blocks on a frictionless inclined plane. rank the situations according to the work done by the forces. In this case, the work done by the forces, since there's no friction involved, since there's no friction, you only have conservative forces. So whatever work you do changes the energy by the same amount. But these blocks are all changing their energy to the same value because they're all going to the same height. Therefore, the forces are all doing the same work. So even though I have a really big force right here, it's going over a shorter distance. And even though I have a little bitty force here, it's going over a longer distance. So they all do the same work. D. Number 15, Newton's second law, is watch your signs. Make sure you get your delta P over delta T. This is F equals delta P over delta T. That's M VF minus VI over delta T. We did one of those earlier, but the tricky part is just watch the signs. Make sure you're getting VF and VI correct and that you have the right sign for them. Okay? And here's a collision problem. I said on the quiz, on the test. Probably a 2D problem like we did for the free response coming up when our exam is in a week and a half or so, 2 weeks maybe.
Yeah, we're gonna choose on the
Yeah, and it's in your workbook too. So it's the very last page of your workbook, but it's on the website, on the course website.
Did you get the sheet? Like, are you going to get us?
Yeah, it'll be, I'll either just print out the section that you need on the front of your quiz, or I'll probably just put the whole thing on the back. Okie dokie. Anything else for me? All right, I appreciate y'all coming. It's useful for y'all to come. I think, right? Useful?
beneficial.
Very.
Huh?
Beneficial
Beneficial.
is the correct word.
Okay.
I didn't think you were